we'll get started. Finish off my mistakes before Saket comes. They're all in the first few slides. Okay. So no. Anyway, just joking. The sooner we start, the sooner we finish. So this is the second in the series of lectures about complexity lower bounds. So if you remember, our first starting point last time was this sort of big picture that we have. We are typically dealing with problems for which we can see n to the k algorithms, okay, where k is, if you will, our choice of parameter. Okay. And our broad, very broad classification was that you it's either FPT or it's W hard. Okay. And now I can freely use W hardness jargon, but last time we focused here. This time we'll go back and focus here. Okay. So we're going to try and get finer and finer classifications inside FPT. Okay. So in the kernel lower bounds, you're seeing one approach to demystifying the complexity theory inside FPT. Some FPT algorithms have polynomial kernels, some of them don't, and this is conditioned on whatever NP not contained in co-NP/poly, or the other way around, whatever. So anyway, so so you have a bunch of hardness results from the perspective of FPT problems not having polynomial kernels. Here we are going to take a somewhat more direct approach, and we are going to say, well, you've seen FPT algorithms with a lot of different running times. We are going to say for some problems, the running times that you have seen are pretty much optimal, assuming again something called the exponential time hypothesis, which has well, I mean, which is a comment about how fast can you solve the satisfiability problem. Okay. It turns out that this is not perhaps as widely or universally believed a conjecture as P not equal to NP, but it's still pretty widely believed. Okay. So we'll come back to what the actual hypothesis is at the very end, but for now let's just work like engineers, and let's just assume that if somebody gave you some starting point, if somebody told you that some problem doesn't have an algorithm of a certain kind, then what kind of reduction machinery do we have to start proving that the problems that we are dealing with don't have algorithms of certain running times. Okay. So so I mean, there is the issue of where I mean, what's the source, what do all these reductions go back to, and so forth. And as it turns out, they go back to the assumption called the exponential time hypothesis, but it's probably worth revisiting that at the very end. For now, let's just try to see what typical reductions look like, and how are they different again from W hardness reductions, and how are they different from no polykernel reductions, and how are they different from NP hardness reductions, which are the kinds of reductions that we have encountered so far. Okay. So so in particular, imagine that imagine that you have a problem which you can solve in time k to the k. For example, one of the first FVS algorithms you saw was a k to the k algorithm, 3k to the k, I think. Often it just turns out that it's not very hard to come up with a k to the k algorithm. Sometimes even that is challenging. But the next natural question is, can you improve it to some c to the k kind of algorithm? Okay, that's a very obvious improvement to ask for. And again, it's the same kind of it's the same kind of philosophy. If you get stuck and you're not able to improve this to c to the k, then you say that, all right, maybe I can't do it, but if you can do it, then something bad happens. Okay. So if you have, so it's going to be the usual reduction strategy. You're going to assume, and we are going to explore in this lecture a few canonical problems that are hard for k to the k, in the sense that k to the k is some sort of a barrier. You cannot improve. So there are no 2 to the little o of k log k algorithms for all of these problems unless the ETH fails. Okay. So there are a whole bunch of problems like this. We are going to, again, for the first half or so of the lecture, a little more, we are going to assume that such problems exist. So here are some problems that are hard for k to the k. I mean that in a loose sense. I mean that if you come up with if these problems have a 2 to the little o of k log k algorithm, then what? Then the ETH would fail. So that's our assumption. Okay. So the starting point is going to be our assumption about problems of this kind. And then suppose you are struggling with a problem for which you are somehow not able to cross the k to the k barrier. If you want to take a break, one of the things you can do is to explore this list of problems in the literature or pick up some from this lecture, and then see if you can reduce one of these problems to your problem. Okay? But now, what would the reduction need to look like? Remember, for W hardness, we said that the reduction can take FPT time, and the parameter has to be constrained to be a function of the parameter that you started out with. Okay? So suppose you start off with a problem that's, let's say, hard for k to the k. So no 2 to the little o of k log k algorithm for this problem. Can you, for example, I don't know. So, for W hardness reductions, we were pretty free with the k. So k would sometimes go to k square, sometimes even 2 to the k, and whatnot. Okay. 2 to the power of k also. Yes. I mean, any function of k was permissible. Okay. Here, however, suppose you start with such a problem. So actually, let's just flash a concrete example of such a problem, perhaps. Let's say I promise you that this problem, which not so surprisingly is a variation of the clique problem, which remember was hard for W1. This is a restricted case for which we have a k to the k algorithm. So what's this restriction? The graph just has k square vertices. Okay, so the vertices, I mean, it's convenient to imagine that the vertices are arranged on a k by k grid. Okay, and you're looking to find a clique that contains one vertex from each row and one vertex from each column. Okay, so in some sense, is there a permutation that corresponds to a clique? Okay, does the problem make sense? So this is, I mean, you can think of this as one of the canonical problems that's hard for k to the k, if you like. Okay. Why does this have a k to the k algorithm? Branch. Okay. Yeah, sure. Yeah, that's right. So I mean, from the first row, it's one of these k guys, so that's k branches. From the second row, it's one of these guys, that's k branches, and so forth. You effectively guess the permutation. I mean, yeah, it would be k to the k by branching. Okay. But for somewhat complicated reasons, this very restricted version of clique is actually stuck with this k to the k running time. You don't expect to improve it. You don't expect to improve it seriously unless ETH fails. Okay, which perhaps is surprising at first sight, but let's go with this as given. Now, suppose I have my problem, some problem x with parameter k. Should I reduce from or should I reduce to? Wait, what? No, I'm trying to show that my problem, let's say it's this problem that I've been working on, and I've somehow found a k to the k algorithm, and I want to say that, hey, there is no, yeah, thank goodness. I was just taken aback for a moment. Okay, so I have to reduce from something like permutation clique with parameter k to my problem where this parameter goes to some k star. Okay, and what I want to say is that x has no 2 to the little o of k log k algorithm unless ETH fails. That's the kind of statement that I want to make. Permutation clique has this property, and if I reduce from permutation clique, I should be moving towards this goal. So what would be the logic? The logic would be the usual thing. Suppose this guy has has a 2 to the little o of k log k algorithm, then permutation clique should have a 2 to the little o of k log k algorithm. But what happens if k, for example, is if k star is some crazy function of k? Does this work? No. It doesn't work even if k is like k square or something. Okay, this already fails. So the restriction and reductions of this kind is that the parameter has to actually be pretty much order k, right? Okay, so you're really restricted now in how much you can blow up the parameter. It's not much. Okay, when k square is kind of dangerous. Do you see that? Because if you have k square, you'll plug in k square here. Okay, and then you don't get anything meaningful, or the kind of lower bound you get is very far from what you want. Okay, you get something like there is no 2 to the maybe I don't know, like this. Huh? Yeah, there's no 2 to the square root k algorithm, no 2 to the k algorithm. I mean, but all those things you probably already believe. You really want to get a tight lower bound. You want to say that this is the best I could do, this is the best anybody can do, unless ETH fails. Okay.
Order k, right? Say suppose I reduce it to 2k.
Okay.
The algorithm becomes 2k whole power 2k.
2k whole power 2k, yeah.
It's not equivalent to k power k, right? It's k power order k.
Well, 2k power 2k is.
Let's write down 2 to the power.
2 to. Yeah, I mean it's easier to write it. I mean see it as k to the power 2k.
K power order.
Sorry. Yeah, I mean it's. I want to see this as. Let me just make sure that that's correct. That's k 2k log 2k. 2k, which is like 2 to the 2k log k plus some constant, which I don't care about. It'll get absorbed in the paper, right? Does that make sense? It's, I mean, it's easier to write down these functions as, for easy comparison, as things on top of 2 so that you can see what's going on. Is that okay?
And also you are comparing asymptotically. So when you say
Yeah.
little o of k log k,
Yeah, I mean,
you're allowing some
yeah.
slope growing functions.
Yeah, some very slow growing. I mean, so basically you're saying you cannot improve 2 to the k log k, I mean, except for up to constant factors, I guess, constant factors on top. Okay, so get rid of this, okay. Okay, I probably have some slides later reminding us of how the parameters are constrained, but for now let's maybe see a concrete example of a reduction. So okay, this is an example of what a solution would look like. And this is our, let's say, just our starting assumption, okay, that permutation clique is one of these hard problems, okay. Now let's say I want to show that permutation hitting set is hard as well, just as a warm-up exercise. It's quite simple. Remember the constraint on the parameter. Other than that, but this won't be very hard here because it's a very similar problem. So you're given, so again, you have a universe which is points from this grid, okay, and you have a family. So these guys are sort of the subsets, okay. So each of the green points denotes a subset. The purple points here, it's not very visible, is also a subset. The orange points are a subset. So essentially, you have a family of subsets from this grid. Okay, and you're trying to find a normal, not a normal, you're trying to find a hitting set which has this permutation structure, a hitting set that picks one vertex from every row and every column. Okay, and I claim that this is, okay, I mean again it's the same k to the k algorithm that will work, but I claim that this is as hard as permutation clique. Okay, so let's go back to the instance of permutation clique and let's try to reduce it to hitting set. So what we want is that the vertices, so it's sort of the reverse. I mean, by the time you ensure that the backward direction works, the forward direction works on autopilot. So let's try to focus on what are our expectations from a hitting set. Okay, so a hitting set we want. So this is similar to something you've seen before. So hopefully this will ring a bell. What you want is that the elements that are chosen by the hitting set shouldn't involve two things. Damn it. shouldn't involve two things corresponding to a non-edge. Okay. The hitting set shouldn't go and pick two vertices that didn't have an edge between them in the original graph. Okay. What should I do to ensure this? Now I've been given an instance of permutation clique, and I have this k by k grid, that's my playground, and I'm supposed to come up with a family of sets. Okay. So what are the things that I should dump in my family to ensure that the hitting set doesn't go and pick two endpoints of a non-edge? So if the hitting set picks these two guys, I should have something in my family that will stand up for me and say I'm not hit. And it's because of this permutation structure that you can actually do something.
For that, you need to have some other vertices
In
one of the subsets.
in one of the subsets that I create, but can you maybe identify which vertices I should throw in?
All other vertex, what is this? Those are the connected to this.
Yeah,
Those are the connected to this.
those that are connected to what?
Clique chooses only one vertex from every row.
A clique will choose one vertex from every row and every column, but I don't know what the clique is going to choose. So what do you mean by choose others? Your construction cannot depend on any clique, right? Your construction has to depend on the adjacencies in the graph. So what I'm trying to encode is that if there is a non-adjacency, a hitting set cannot afford to pick both endpoints of that non-edge. Okay, so what about I throw in this set? Okay, for this non-edge, so every non-edge is in, let's say, is cutting across two rows. Okay, for those two rows, I create a set which contains all elements of those two rows except for these two.
This you're doing for an edge?
For every non-edge.
The red one is a non-edge.
Yes. Okay, is this making sense to everybody? So what happens if you have a permutation hitting set? Why is it going to be a clique? Suppose it's not a clique. Okay, then there is an edge that's missing. But for every missing edge, there is the set in the family. Okay, and why can this set not be hit by anybody else? Yeah, because sorry.
Pick that, you would not have picked the others.
If I would have picked that, I wouldn't have picked the others. Okay, sure, yeah. So, okay, I see what you mean. So, yeah, because it's a permutation hitting set, right? Because it's a permutation hitting set, you have picked these two guys from these two rows. So, you have kind of lost your chance on these rows. You're now not allowed to pick anything else from these rows. Okay, so from every row, you're allowed to pick only one vertex. Okay, so the only hope you had for hitting this particular set is gone. The set is not hit from anywhere else. Okay, so that's why a hitting set has to form a clique. But does this remind you of something though? We did a very similar construction when we were doing, I don't know, when we were going from independent set or clique to dominating set. And I mean hitting set, dominating set, really the same thing. So we wanted to say that elements of the dominating set should go back and form an independent set. So we said that whenever there is an edge, we are going to introduce some vertex which will not get dominated if both endpoints of that edge are not chosen. Okay, so some ideas are a little bit, I don't know, not universal, perhaps too strong a word, but sometimes similar ideas keep coming up in different contexts. Okay, so this is sort of again a generic gadgeting trick. Okay, so you want to ensure that the hitting set forms a clique, throw in a set that's not hit for every non-edge. But sometimes it can be tricky to do this. We have to make sure that the forward direction works as well. So why will a clique hit every set? Mm-hmm. Correct. I mean, you can essentially show, but because of the very special structure of the permutation problem, that if a particular set is not hit, the set has a very specific form, right. Set is essentially all elements across two rows except for a pair, okay, right. And if this set was not hit, it means that this pair that was missing from the set is precisely the two elements participating in the clique, okay. But then this was not an edge. That's the only reason you would have had that set in the first place, but you're staring at a clique, so that's the contradiction. Is that clear? Okay, so it's essentially the same argument that works in the forward direction as well. Okay, so what happened to the parameter? Yeah, it's preserved exactly. K goes to K. So you show that permutation hitting set also doesn't have a doesn't have a 2 to the little o of k log k algorithm. This is the this is the counter example for the clique. If the green vertices are a clique and there's a set that's not hit by it, then there is necessarily a non-edge in the clique, which is the contradiction. Okay, all right. Okay, this is not working. Okay, so we're going to look at an even more restricted version of permutation hitting set. Which also turns out to be hard. Okay, we will not get into the proof of this because it's a bit involved, but permutation hitting set with the additional restriction that every set picks at most one vertex from each row. Okay, so now the sets cannot be any arbitrary subset of this universe. The sets are themselves restricted to pick at most one vertex from this row. Okay. So, even this restricted version of permutation hitting set, where the family has some special properties, okay, turns out to be as hard as the original problem. Okay. The reason I am introducing this is because we will use it to show a lower bound for a problem that you have seen before. So, that will give us a little more practice. So, but is the problem clear? It's the same problem. I mean, you still have to find a permutation hitting set, but now you have the additional constraint on the family. The family is more structured. The family, every set in the family picks at most one vertex from every row. Okay. So permutation clique was hard. Permutation hitting set is hard. It turns out that you can go from permutation hitting set to permutation hitting set with thin sets. So every set has size at most. Every set in such an instance has size at most k. Yeah. So that's perhaps the reason for the name. Was that the reason for the name?
Okay.
That the sets are not too big? That's the name, yeah, I don't know. That's the name in your book, and I think even in your paper.
But not in the paper, so I didn't do.
Okay, all right. So, fine. So, what's the problem for which we are going to show hardness? This is a problem that you've seen, I think, during the ILP lecture, closest string. So, the input is a collection of n strings over some alphabet A. Okay, all strings have length L. Okay, and you want to know if there is some string which has the property that it's close to every string in this set in terms of the Hamming distance. So, you take the question is there a string of length L such that for every string in this set, the Hamming distance between this string and xi is at most d. Okay. So, that is the closest string problem. And it turns out that closest string also has an algorithm with running time d to the d, and also I think alphabet size to the d. Okay. These are, I don't know, the lecture notes claim that these are two nice exercises, so maybe think about it. But this is a lecture about lower bounds, so we are going to say that if you manage to solve these exercises, you have actually arrived at the best possible algorithm, unless ETH fails. Okay, fine. And we are going to reduce from permutation hitting set with thin sets. Okay. Okay. Fine. Now I'm going to encourage you to think about this a little bit because it's a fun reduction. Notice, let's just recall what are we constrained by. We want to show, for example, no d to the d algorithm. I mean, nothing seriously better than d to the d. So d, that's the number of mismatches that you allow between the given strings and the string that you're looking for should be a function of, should be just order k. Sorry, you had a question? Not particularly. This is an out of scope reduction. Yeah. But you show it's hard by just a reduction, just as well. Closest string definition. It's not much on the. Sorry, that should be length L. Is there a string of length L over A? A string of the same length as all the given strings. So I'll actually tell you that D is going to be k minus 1 and A is going to be k plus 1. So you'll actually end up showing that both of these algorithms are pretty much optimal. Okay. Are you okay with this? All right. So let's just, I don't know, maybe stare at this a bit. What do we want? We want a hitting set. So we want the string that's the closest string to somehow give us a hitting set. Okay. So what's the intuition? So the thing that's in my hand is the distance, right? What is the distance? So if the closest string is supposed to be okay. So the strings, right? The strings that you generate x1, x2, up to whatever xn. These strings sort of represent constraints, right? And our constraints here are these sets that need to be hit. Okay. So it may be natural to think that for every set you should somehow have a string which is encoding the demand that I need to be hit, and the closest string should somehow, the closest string just by virtue of having not more than d mismatches should hit this set, hit the string that you generated for this set. Okay. So let's first of all have sums. So for every set in the family, so let's say F is the family. So for every set in the family, we'll plan to have some strings. Okay. And then of course you need to encode the fact that the things that you pick form a permutation, but we'll come back to that. That's a structural thing. Okay. But for now we want to say that, okay, I mean, so let's look at the green set, for example. So in the first row it occurs at the, so let's decide on the alphabet, right? So the alphabet I somehow want to be k, and I want this string to somehow tell me what should I pick.
You also want to have an alphabet.
What do I, so if I have a solution to closest string, right? The string should lead me back to a permutation hitting set, right? So at least the most naive way of trying to encode this is to again have an alphabet which corresponds to locations. Okay. So if the alphabet is 1 to k, my semantics will be that if my string is something like 3, 4, 1, 3, 2, 5 or something like this, okay, then I'm going to interpret it to mean that from the first row pick the third element, from the second row pick the fourth element, and so on and so forth. Okay. How do I make sure that the string doesn't take me to picking two things from one column, etc.? We'll come back to. We'll try and ensure that in the next step. But for now, this is sort of the base semantics. Okay. So what happens? So I should make something go wrong if, for example, none of the positions corresponding to x1 are chosen by the string. Okay, and notice that we have thin sets. So x1 is occurring exactly once in every row. So this guy here in the solution is telling me what to pick. From row I, okay? That's what the ith column is telling me. I mean, that's how I want to design this thing. Okay, so what should I put here so that if this string takes me to a set that misses this set completely, okay, it takes me to something that's not a hitting set, then somehow these strings should be fine. Okay, they should have a lot of mismatches. So for the first set, okay, let's say that's the green set. For the green set, what should I throw in? So I have 1, 2 up to k, a string of length k. There is a pretty natural thing for what I should put in at the first location, for example.
4 star 3 5 5 5.
Yeah. Do you see why? Not you though.
Start because nothing is there inside.
In the second row, yes. Okay, is everyone sort of getting the hang of this at least? So what's going on? So instead of thinking of it as at most so many mismatches, let me just say that these are strings of length k. Okay, I want to close a string that has at least one match. Okay, that will translate to at most k minus 1 mismatches. Okay, so the moment I have a match, this set has been hit. Okay, that's the kind of thing that I want. The moment I have a match, the set has been hit. Okay, so if this guy is saying pick 3, and when will x1 be hit if 3 is picked? Provided x1 is actually sitting at the third location, right? So I'm just going to put in the locations of these sets in all the rows in my strings. Is that making sense? Okay. So for example, for the orange set, I've put in 1, 3, 2. Okay, there are no appearances here, no appearances here, and then there is a 1.
Oh, the star is.
Yeah, the star is just to count for a sort of no show. Yeah, there is a no show, and because we'll be encoding the permutation, you'll never get a star in the hitting set anyway. But that's for later. Okay, so I do this for every set. Okay, so for the green set, it's I think what Arjun was suggesting, 4 star 3 5 5 5. Okay, so now suppose let's forget about the permutation aspect of this. But suppose you give me a string that has at least one match with all of these strings. Okay, in other words, it has at most k minus 1 mismatches with all of these strings. Yes. No, this grid is now a universe, a family of subsets over the universe k cross k. Okay, right. No, I have a universe whose elements are ij pairs, I going from 1 to k, j going from 1 to k. Okay, and I have a family consisting of sets which are subsets of this universe, where you have at most one element of each first coordinate.
Are you given that those subsets are disjoint? Like your
No.
diagonal is disjoint?
No. I just didn't want to clutter it. But they don't have to be disjoint. No. They just have to pick at most one guy from each row. That's the only constraint. But it doesn't hurt if they are the same. I mean, you just get the same guy on different rows. Yeah. Okay, so what's the construction of strings so far? For every set, you're going to have a string of length k, which basically tells you the first position tells you at what location in the first row does this set appear. Okay, at what location in the second row does the set make an appearance? okay, and so on. There are some rows which may not intersect with the set at all, okay, in which case you will just have a star. Okay. So, suppose I give you a string with at most k minus 1 mismatches with all of these strings. I claim that if you just follow the string, okay, so I go and pick, so the string is telling me go and pick the third element from the first row, go and pick the fourth element from the second row, and so on. Of course, this is a bogus example, but if you just follow the string, you will have a hitting set, because if you didn't, I mean, you may not have a permutation hitting set, okay, but you will have a hitting set in the following sense. Suppose there is a set that is not hit, okay, then you look at the encoding of that set, okay, that is going to be missed entirely. Okay. Every location is going to be a mismatch, because if there was a match, then that means that, well, that was, I mean, you had an element of that set at that position, and the string has asked you to go and pick the element at that position. So, the moment you have a match, that means that the string corresponding to the set and the location dictated by the closest string have patched. Right. So, the string may contain a star, because that is a part of the alphabet, but once we ensure that the string is a permutation from 1 to k by doing some more work, then that will not happen, because there is no space. It has to be a string of length k, right, and if the string of length k has to be permutation of 1 to k, then there is no space for additional symbols.
So, are you saying that the string that we are looking for,
Yeah.
whatever is hitting it, it should not contain any special cases?
It should not contain any, the string that we are looking for should not contain this, the star character, yeah. Okay, now I just want to ensure something very simple. For 1 to k, for each alphabet in 1 to k, my string should contain at least one occurrence of each of these characters. That is enough, right, because the string is of length k, it will automatically contain exactly one occurrence of these characters. Okay. So, let us focus on 1. I want to make sure that my solution string contains at least one character. What should I do? I mean, I am free to introduce more strings here, of course. So,
Match with the others and at most.
so
Introduce more strings among them, whatever is the answer should also match with the others.
correct. I mean, it is precisely that. I mean, that is what I am going to use to say that my string is going to have a certain form. And in the forward direction, it will work because you are starting with a permutation hitting set. So, I mean, you will see that.
Okay, so put one in
Column, one element from first column.
No, I am saying that, so you know that you have to pick, I mean, because it is a permutation hitting set, all numbers from 1 to k have to feature in the hitting set, right, because you are not allowed to pick, the second position here and the second position here, for example. Right.
Introduce k minus 1 factorial strings with one at the first place and all of them in the second place and all of the third place.
Am I even allowed to introduce k factorial strings?
Have k more strings with all ones all
No, but are you allowed to do k factorial strings? Just imagine.
Because
what goes wrong if you introduce k factorial string? Your running time.
no, parameter will be k. Parameter will still be k, but you still cannot
but
introduce k
you have already
factorial
taken
strings.
k power k time to come to this input. So if I even get a better algorithm for this, I mean, what good is this?
Right, because to make the argument go through, you have to run the reduction first, right? That has to happen in some, yeah, that has to happen in 2 to the little of k log k. So you cannot introduce k factorial strings even if your parameter is going to be k.
So, do you look at the minimum length subset in the family and k minus the length of that set, those many extra?
Okay, all right. Sorry. Okay, now there is something simple that you can do. I guess a couple of people have already seen it. So, if I want to ensure that there is at least one 1, then I have to introduce a string which is mismatched everywhere if you do not put in a 1. Okay. So, if I just put in, okay, was that a not so nice way of saying it? I do not know. Okay, so let us just do this. Let us put in a string with all 1s, all 2s, all 3s, etc. Okay, these are just k strings. Okay, once you do this, suppose you have a solution that doesn't contain 2, for example. Okay, then what's happening with the all 2s string? What's happening with the all 2 string is that it has no hope of getting matched. So, it definitely has k mismatches. Okay. So, if it has k mismatches, then it is not a yes instance. Okay. So, the string that you generate will automatically be a permutation of 1 to k. It will also be a hitting set because of the way you have encoded the sets themselves. Okay. And in the forward direction, what is going on? You have a permutation hitting set. So, definitely 1 to k completely feature in the string. So, these guys have at most k minus 1 mismatches. In fact, they will have exactly k minus 1 mismatches. Okay. And down here, everybody will have at least one match because these sets were after all being hit by the hitting set. Okay. So, wherever the hitting set, so you look at the green set for example, the hitting set picked up a green from somewhere. So, let us say it was here, then that is the position that will be common between those strings. Okay. Is this clear?
Suppose in the green set,
Hmm.
say that sixth row element was not there,
Was not there. Okay.
So then do we need to add the string for 666?
Well, I mean, first of all, I think you can always ensure that for every row there is a set containing at least one element from that row. Well, I mean, it has to be k by k and so forth. So, but I mean, you know, let's just assume that we have a nice instance. I mean, we have a serious instance where you have at least one element from each set from in every row and every column. Okay. So I mean, no row or column is empty when you look at it with respect to sets. Yeah. So, I do not know offhand if you can delete a row because you get a k by k minus 1. So, yeah, you have to worry about that a bit, but yeah, okay. All right. Okay, so that shows that both these algorithms. So, notice that the alphabet size that we used was just k plus 1, the number of guys here plus a wildcard character. So, both of these algorithms are essentially optimal. Okay. All right.
If we don't have this with thin sets, I mean, just if we want to reduce from permutation hitting set,
Right.
I mean, can we just instead of each string having being k linked, or it will be k squared linked?
Potentially, like order k squared at least if. I mean, at least this style of reduction doesn't work. You may be able to come up with something else, but unlikely. Yeah. Yeah. Okay. All right. Sorry, you were saying something.
It took 3 months to come from where
Right.
it's
Okay. Okay. Sure. All right. So moving right along, let's conclude. This is the best that you can hope for as far as closest string is concerned because permutation hitting set was hard. And let's go back a little bit and talk about a more relaxed version of permutation click, for which I can perhaps show you a little bit of evidence for hardness. Okay, maybe not the full deal. So it turns out that you can go from this problem to permutation click. So I'm doing this a little bit in reverse. So what's this called? This is just called k by k click. So remember that permutation click, which was a very useful problem in terms of being very restricted and constrained and so forth, we just assumed is hard. Okay. So I mean, I gave you absolutely no serious justification. I just told you that assume that if there's something better than ETH fails, but there was no evidence. Here, however, we will show a little bit in terms of evidence by showing that a classical problem called 3 coloring reduces to this guy. Okay. So here we will have some reason to believe that this guy is perhaps hard, and from here to here is again a somewhat complicated reduction, but it's kind of there in the notes. But actually what's there in the notes is a randomized reduction, which is possible to understand, and then it apparently can be de-randomized, but I don't think you guys go into it using hash families and so forth. I mean, yeah, so whatever. So, but there is I mean, eventually you can, there's a proper deterministic reduction from k by k click to permutation click. What is k by k click? It's a lot like permutation click. You still have vertices arranged on a grid, okay, but you don't care about repeating vertices across columns. Okay, so you just required to pick one vertex from every row, from every row. Okay, I haven't quite thought about, okay, all right, fine. So we'll have just about enough time to go through this reduction. So let's say again that we know this, okay, and the reason we know this, I mean at the end when we state ETH, you will be able to go and verify for yourself that we know this. I guess this is one of those textbook reductions that we were talking about. So if you look at just the well-known reduction, yeah, I'm going to state the sparsified version of ETH anyway. So I mean because it's too complicated to. Okay, so we are going to state, yeah. So the way we are going to state the exponential time hypothesis, which is equivalent to the way maybe the way it was stated when it was first stated. The way we are going to state it is a somewhat simplified version. Once you assume that that is indeed the hypothesis or an equivalent formulation of the hypothesis, you can go back and verify for yourself that 3 colorability is something that cannot be done in better than 2 to the little o of n time. But just as a sanity check, do we have a 2 to the n algorithm for 3 colorability? You are just checking if the graph has a proper 3 coloring. So we all know that it's NP hard. It's the NP hardness reduction that I'm encouraging you to go and double check to see that the parameters translate the way you want them to get this ETH kind of hardness. But I claim that this is also a tight result, I hope. So this should be quite easy. What's a guess one color class and the rest is bipartite, okay. So 2 to the n. So 3 colorability has has this tight situation. Now we want to show that you cannot solve k by k clique in 2 to the little of k log k times. So what should n go to? When I translate, now I'm translating, now I'm translating from a classical problem down here. Can n go to k, for example? Is that good enough? Sorry, what I mean is, yeah, can k be n? Is that good enough? I mean, you're going to generate an instance of k by k clique. So you started from a graph problem. So you started from colorability, 3 colorability, sorry. So you started with a graph G on n vertices. That's the size of the input. Let me not even worry so much about how many edges are in there. And I want to reduce to k by k clique. As you can imagine, k is going to be some function of n, right? So previously, for example, if we went from k to order k, we were good, right? Here similarly, is it okay if k is equal to n or order n? It should be fine. Okay, so let's see how we would prove hardness for k by k clique if 3 coloring is hard. So if k is equal to n, right, then so what would the argument be? Suppose there is a 2 to the little o of, okay, I guess the easier way of saying it is that if k is equal to n, then you don't expect a 2 to the little o of k algorithm for k by k clique, because k is equal to n, right? So you just, I mean, this is an argument that pretty much follows by substitution, okay? Because if k, so you translate k exactly to n, let's say, then the conclusion you arrive at is that you cannot do k by k clique in 2 to the little o of k. For example, there is no sub-exponential algorithm for k by k clique, like 2 to the root k and so forth, okay? That you definitely get because of such a reduction. But notice that that's not what you want, right? You are much more ambitious than showing that there is no 2 to the little o of k algorithm for k by k clique, okay? So here's where you are. You have a k to the k algorithm for k by k clique. Notice that it's the same algorithm. You have to pick one vertex from each row. So you just branch. So you have a easy k to the k algorithm. And what you really want to show is that this is the best that anybody can do. But if you plug in k equal to n, then all that you can conclude from that reduction, irrespective of how much effort you put into it, is that there is no 2 to the little of k algorithm, and this is a big gap. Okay, picture not to scale at all, this is a big gap. Okay, so that's not a very useful result, and you want to get much closer. Okay, so let's go back here. What should k be? Should it be something more than n or less than n? Yeah, it should be something smaller than n, right? N is already too big. Okay, so you can't afford to take k to, you can't afford to reduce to an instance of k by k click with k equal to n, even that's already giving you too weak a hardness result. Okay, so k has to be smaller than n. How much smaller than n do you think is enough? I mean, any suggestions? N by log n. Yeah. That's a natural thing to try. So if you just do, this is what you want. So you plug in k star equals n by log n. Then what you get is that the log n on top essentially cancels, and you go back to 2 to the little o of n. Okay, which is the condition. So suppose you had, so k star is what let's say you get, okay, and if k star was something like n over log n, then if you had a 2 to the little o of k log k algorithm, that would imply a 2 to the little o of n algorithm if k was log n. Okay, if k was n over log n. So that would be n over log n times log n minus something. The log n would cancel, and it would be 2 to the little o of n. So you want to shave off a factor of log n as you go along. Okay. Just a quick exercise before we see the sketch of the reduction. This was a fairly interesting and technical paper for those of you who want to look it up. Edge click cover is this nice problem that we have perhaps not discussed. So you want to cover all the edges of the graphs with k cliques. Okay, I think at most k cliques, right? So so again, this is a cover, not a partition. For I think partition, the question is I think easier. The difference between, so does there exist a cover, okay, S1 to Sk such that each Si is a clique and every edge in the graph belongs to some Si. So you want to cover the edges of a graph with at most k cliques. You don't care if the cliques overlap, that's okay by you. Okay. As it turns out, and you can also define the same problem but demanding partitions. Okay. And it's actually a nice exercise to check that the partition version I think actually has a polynomial kernel, but this guy has a very cute and simple 2 to the k kernel. Okay. What sort of a FPT algorithm does a 2 to the k kernel give you, if for this sort of a problem? Okay, if you just had to brute force, I think this is, if you do brute force, it will be like k to the, 2 to the k log k, but because here, no? All partitions.
You have to guess the click.
Correct.
Right?
So for every,
guess a click, which is so 2 power k just for guessing a click, right? It could be of huge size.
that's right. But I'm saying that, no, I'm saying that for every edge in the graph, and there are at most 2 to the k edges in the graph, I'll guess one of k labels.
No, there are 2 to the power k square.
Okay, I see. Okay, fine. I didn't take that into account. So I thought it was an instance kernel.
So this problem can be solved in time 2 to the power n, where n is number of vertices. Hence, it can be solved into power 2 power k.
I see. Okay, but it's not an instance kernel. That's what you're saying. The number of edges is 2 power k squared. It's not an.
We only count number of vertices.
Okay, we only count number of vertices. Okay, all right. So mistaken there. So let's just say that it turns out that you can solve this problem in 2 power n time. Okay, so if you have a kernel of size 2 power k, then you have a 2 power k algorithm. Okay, fine. And it's actually shown that this pretty, I don't know, non-impressive looking running time is actually the best that you can possibly achieve under ETH. Okay, so just as an exercise, okay, this is a fairly, it's a fairly lengthy and complex reduction, but what should the k star be if you want to show a result like this? Notice that this is a very ambitious lower bound result. You are saying that you cannot do better than 2 power k, in the sense that there is no 2 power little o of 2 power k algorithm. Okay, and these guys reduce actually from 3 sat on n variables, which also you can assume, let's say, doesn't have a 2 to the little o of n algorithm. Okay, so what should k be as a function of n? Log n. So k should be log n. So you should start with a sat formula and reduce it to edge clique cover. First of all, ensuring that satisfiable if and only if you can cover with k edges. I mean, that's always the heart of the matter. But you're only allowed to use, so if you start with a formula of length n, I mean involving n variables, then the budget that you're allowed to use is only log n. Okay? How many times have you seen a reduction where the parameter in question goes down? I mean, at best it stays the same, or it increases. I mean, usually you need it to increase to make the reduction go through. So these are reductions that are a lot more challenging in what they are trying to achieve, but the conclusion is correspondingly strong. You are now ruling out, you are now saying that nobody can do better than 2 to the k. So you come and tell me it's a horrible algorithm, I'll challenge you to do better than this. Okay, so
just to point, actually all of these are all these are polynomial time reduction.
right, they don't even use sub exponential.
Polynomial time reduction. It's just that they are much tighter reduction in terms. It's not that we are using any like fancy running time to come up with no. Almost all of the reduction are actually normal polynomial time reduction coming with this to coming with this.
Right. So although technically I guess you could spend sub exponential time
All
to
that
come
much
up,
time.
yeah, I mean whatever time you're trying to beat, you can spend that much time to come up with a reduced instance. So what Saket's pointing out is that it just turns out that these reductions are just pure polynomial time reductions. So the definition, these reductions are different from NP hardness reductions in two ways. One, it gives you more freedom in the running time, but it kills you in having restricted the parameter very badly. Okay, so you would think that these reductions take advantage of that freedom to compensate for this difficulty, but they actually don't. So they take no serious advantage of this running time freedom. I don't know, it's perhaps interesting to see if there are simpler reductions that take advantage of that aspect of the definition, but most of these reductions that we have already are just these polynomial time reductions, purely polynomial time reductions that manage to really crunch the parameter in a way that you can conclude a lot more about the algorithm than just saying something like not FPT or not whatever. Okay, fine. So let's just see a glimpse of the reduction from 3 colorability to k by k clique. The parameter. So if you're starting with n vertices, you're going to go to n over log n. Okay, that's the kind of translation. You fix k. So there's going to be a little bit of, I mean, obviously, as you can imagine, you'll have to muck around with the parameters to get everything right. And I don't really want to go so much into the math, but to just give you the spirit of the reduction. Okay, so so what you're going to do is partition the graph into k parts, where k is something like 2n over log n to the base 3. Okay, and we'll see where the base 3 comes in. Okay, so this is just a arbitrary partition of the graph. You just list the vertices, and every time you encounter how many. So your k is 2n by log 3n. So every part is how much? The part is something like n over k, right? So n over 2n by log 3n. So every part has size roughly log 3n by 2. Okay, so you just list the vertices. Every time you hit log 3n over 2, you put it in one bucket. The next log 3n over 2, you put it in the next bucket, and so on, and you generate something like VK partitions. Okay. Now for each part, okay, for each part, what I am going to do is I am actually going to enumerate all valid 3 colorings of that part. Okay. So, I am going to have a vertex. I mean, of course, I am reducing from 3 colorability to k by k clique. So, I need to generate that k by k grid. Okay. I already have k columns. Okay. And you can check that, okay, how many 2 colorings if every part has size log to the base 3n divided by 2, how many 3 colorings are there of these many vertices? 3 power this, which is just square root of n. I mean, it's just square root of n, isn't it?
Yes.
Yeah, good. All right. So roughly square root of n many 3 colorings for each of these parts. Okay, and you can actually verify that square root of n is at most k, otherwise n is going to be a constant. That's just by rearranging this equation a bit. So, so the number of colorings is going to be at most k because of the way k is defined. If it's the other way around, n is going to be bounded by some stupid constant. Okay, and then you can just solve it just like that. Okay, you don't have to worry about anything. Okay, so so the number of colorings is also bounded by at most k. If it's not exactly k, you generate some junk coloring so that it comes up to k. Okay, so I mean, not junk colorings, is duplicate some colorings so that it comes up to exactly k. So for each part, you're going to have, so you're going to have a vertex in your grid for each 3 coloring of that part. Okay, so that's your k by k grid. Every vertex semantically corresponds to a 3 coloring of some of one of these partitions. So the ijth vertex corresponds to the jth 3 coloring in your list of 3 colorings for the ith part. Okay. What do you think the adjacency should be? If I want to go from 3 coloring to clique, when do you think I should put an edge between 2 vertices corresponding to 2 3 colorings? In particular, I don't want the clique to, so I mean, as you can imagine, what I am trying to do here is that whatever vertices are chosen by the clique, I want to pull that back to a 3 coloring. Okay, the most natural 3 coloring I will pull back to is by saying whatever 3 coloring you gave here, that whatever 3 coloring was chosen here, that's the coloring you give to the vertices in this part. Whatever was chosen here, you give it to this part. Okay, so the clique shouldn't choose 2 3 colorings which are somehow incompatible. Yeah, when are 2 3 colorings going to be incompatible? I mean, this 3 coloring says this vertex is red, this 3 coloring says this vertex is red, but in the graph these 2 vertices have an edge between them, stuff like that. Okay.
How will that work? Just the thing that you just said before that.
What did I say just before that?
Why are we
Okay, so now maybe let's just complete the semantics of the edges, and I think hopefully it will be clear. The grid, so for every 3 coloring of V1, okay, I have a vertex which says, which is labeled by that 3 coloring, let's say, or which is indexed by that 3 coloring. Okay, okay, so for the number of rows, right. So how many rows are there? There are as many rows as there are 3 colorings of V1. Okay, and it's possible that there aren't k 3 colorings. It's easy to show that there are at most k 3 colorings because of the way the sizes are designed. Okay. Pretty much, yeah. I mean, you can imagine that the first vertex that I introduce in the grid has a label which indicates what that 3 coloring is essentially. It's just one vertex, yeah. So this entire thing, maybe the next picture is clearer. I mean, this is just one vertex corresponding to some 3 coloring. Okay, this is just one vertex corresponding to the next 3 coloring, and so on. Okay, but I want to throw in these edges when I know that if I try to impose this 3 coloring on this, I try to impose this 3 coloring on this, it doesn't extend to a 3 coloring. Okay, that means that these 2 3 colorings are somehow assigning colors in such a way that there are some monochromatic edges going across. I mean, of course, they are locally valid 3 colorings, but if going across they are not valid when put together, then I have then I don't have an edge, sorry, whatever, I mean, so you get the point. So whenever two colorings are compatible,
Just repeat some colors.
repeat some colors. I didn't really mean to say junk, I
Just
meant
Same
duplicate some
color,
colorings.
just add.
So if you're short by a certain number,
What
take.
was that? Okay, even if you repeat some colors, my point was that
What is
finally
the-
I'll need a click. So finally I'll need a coloring such that it's from each row and each column.
Exactly.
But
Yes,
So-
so what?
So anyway, you throw in the adjacencies between every pair of
It's
colorings.
improving. Just think. It doesn't require anything more. Just think.
Okay, what's trickier in your, according to you, forward or reverse? No, you're done. Okay, all right. So okay, so this is my proposed grade. Okay, and suppose the graph was three colorable, right? This is the construction. That's it. I mean, you just add edges between two vertices if they're compatible as colorings. Okay, so so suppose you have a three coloring, right? Just project those three colorings on each of the paths. Okay, and since you had an exhaustive list of three colorings, okay, this projection is somewhere on this list. Okay, and you can just go and pick it up. Okay, I mean, imagine this matrix sort of rotated, because I mean the requirement was pick what, at most one vertex from each row, right? I'm picking pick one vertex from each row. I can repeat columns. Here I'm repeating rows. It's the same thing. Just turn the configuration around in your head if it really bothers you. But for each column, I'm going to go and pick a coloring. Okay, it's possible that sometimes I may pick the second coloring here and the second coloring here. Okay, so I mean, it's in the rotated matrix, it will be one from each row. Okay, so it's the same thing. In the converse, if you have a clique, that naturally leads you to a coloring of the vertices, and that's going to be a proper coloring, because if it was not, there was a violation, and somewhere there was a non-edge in your clique, which is the contradiction. Okay, so conceptually the reduction is actually not very difficult to see. I mean, the correctness is easy to see. The funky thing is about the getting the numbers right, partitioning vertices in this way, and actually being able to draw this conclusion. Okay, so notice that the number of vertices on the grid is actually n over log n. Okay, and that's the important thing for you to be able to conclude that k by k clique cannot be done in 2 to the little of k log k time unless ETH fails. You need to really have a hold over that parameter. If you think this is kind of straightforward, then I would encourage you to try and do this for clique to show that. Okay, what do you expect to show? Showing something like 2 to the little of k log k isn't a big deal for clique, because clique is not even, it's not even FPT. Okay, so you don't even have a k to the k algorithm, so this is not even going to be a tight result. But for clique, what you can show, you can actually show that there is no f of k n to the little o of k algorithm unless ETH fails. Okay, so of course you can do n to the k, that's again simple branching. Okay, or just try all possible k size subsets, it's effectively n to the k. But if you wanted to get n to the little o of k, you're going to get into trouble unless ETH fails. And in fact, no matter what computational power you get from the side, for any f of k, you don't expect f of k times n to the little o of k. Okay, unless ETH fails for clique. And in fact, the reduction is very similar. You start from 3 colorability and you do this kind of partitioning of vertex sets, but now you have to keep track of. I mean, now it's not really k by k clique. Okay, so although conceptually it's still about partitioning vertices and it's still about enumerating 3 colorings and drawing these adjacencies, those aspects of the reduction are exactly the same, but the numbers are a lot messier. So if you found the previous reduction straightforward, then I'd encourage you to try this out as an exercise. It's still not impossibly difficult or anything, but it requires a lot of careful thought, because notice, for example, I'm saying that no matter what computable function you give me, you won't be able to get an algorithm like this. So you have to think about it a little bit more. But notice that one consequence of this is that, so in particular this is saying a little more than there is no FPT algorithm, but in particular it's saying there is no FPT algorithm, right? FPT algorithm is very far away, because here that's in fact restricting you even more. That's saying there should be a constant up here. So if click had a FPT algorithm, then, well, in particular W1 would collapse to FPT because click is hard for W1, and if that happens, certainly ETH would fail, because ETH keeps you from algorithms like this. It keeps you away from FPT algorithms for click and even stronger algorithms for click. Okay, so that's one of the assumptions on which the W hierarchy is standing on right now. It's ETH. Of course, I haven't given you a proof, but the reduction in spirit is similar to what we have seen, and of course, you have to work out the maths. The maths, if you're curious, is in the notes. So it's about a one page argument, so you can go over it. It's quite doable. Okay. So that just brings us to more or less the conclusion. We know that we now know why we believe that W1 and FPT are separate classes. If you believe that ETH is true, so but we've been going on and on about ETH without telling you what it really is. So let's break the suspense. ETH is the following statement. It says that you don't expect to solve 3-SAT in 2 to the little o of n plus n time. Okay, this is a very refined version of ETH. The original statement is a lot more mathematical, and to get from the original statement down to this simplistic remark about what you can do with 3-SAT, you need slightly heavy machinery in terms of what's called the sparsification lemma, and there is some history as to why people actually believe this statement, but there is a stronger statement that people may or may not believe as strongly, which we will come back to in tomorrow's lecture and see what it means for us, especially in the context of algorithms that do dynamic programming over bounded tree width graphs. We'll see that you can get a lot of tight results there as well, based on what's called the strong exponential time hypothesis. Obviously a stronger assumption to make, but you also get a lot of exciting lower bounds out there. So that's what we will do tomorrow, and with that we will stop here. Thanks. हाँ क्या है, फिर आप तो बोलते हैं बोर्ड पे लिखो तो मैं सोचती हूँ